requires, let's say some company person, a manufacturer does it, we simply ask them, I need a gate which takes a input value X, converts that input value into, or feed that input value X into some function. That functional value it imparts onto a target register and gives us the output. This is the function or a functional gate would look like. So if that kind of a thing would exist, in that case, what we can do is bunch all the input values which we want, like argument values of X, we want to read and feed it to the functional, some function, find the functional values, not just functions, we want to find the sum of functional values. Okay, so such thing is possible, right? So such thing is possible with a Dutch algorithm. We saw that in the last session, you see. Okay, it's simple section, part by part quantum information goes through a gate, the functional gate, and then at the end, by analyzing the output of this functional gate, we can easily make out whether we are getting a sum of the functional values or not. For a specific scenarios I gave you, but it can be generalized to a large number of inputs. Okay, so what you see in the final box, just by reading or analyzing the query register, you see the query register is the top one, right? So once it comes out, by just reading the query registers information, we can make out the f of x value and f of x plus some other f of x values. You see the target register is there as it is. Okay, so interestingly, query register acquires the information of the functional value sum. Okay, so this is a Dutch algorithm for you, and then we introduced a Dutch Joyce algorithm in the last class, last session. So there we did mention that a kind of a game it would be between two people, like two people, let's say Alice and Bob is there. Okay, Alice is entitled to create some information, share that information with the Bob. Bob would process that information, and Bob returns back the processed information to Alice. Okay, so here in this case, okay, let me go back to head mode. Okay, let's say Alice picks a set of numbers, some random numbers, let's say from 0 to 2 to the power of n plus 1. Sorry, 2 to the power of n minus 1, because we want just 2 to the power of n numbers. Let's say Alice picks these numbers, okay, and Alice, okay, Alice is there already, and let's say she shares these numbers with Bob. Okay, let's say Bob somewhere else, and Bob takes the numbers. Maybe in what form she sends? Maybe she sends in the form of, let's say, an SMS or a mail or something. Or let's say she makes a phone call and communicates, right? So what Bob does, Bob takes, okay, so all those numbers, okay, X, I'm representing the set of numbers between 0 to 2 to the power of n minus 1. He takes those numbers, feeds to a function which is using in the first place. So one constraint for him is he should use a function which is, okay, right, which is, I'm sorry, I can see my microphone changing, audio is going. Okay, so audio, if somebody having audio issue, please cross check. Okay, right. So Bob must use a function which should look like a constant, means for all x it is 0, or 1. That is a constant function for you. Or this function would take 1 or 0 for half set of values of x. For half the set of values it takes x, for remaining half it takes 1. Okay, so that is a balanced function for you, right? So Bob must use this kind of a balanced function, or sorry, this kind of a function. But like it can become a constant or it can become a like a balanced. Okay, so the question is now only Bob knows what is this function. Okay, right? So what Alice does is she picks a number, let's say 0, sends to Bob, and Bob feeds to his function f of x and gets the result. That result he will send back to Alice again in return. Okay, right? And Alice reads that f of x function, and she will notes down. Let's say what she does is, okay, she takes x value, send it to Bob. Okay, so Bob feeds, and let's say 0, let's say he will get some number, something which I don't know, and that is written to Alice. Alice will find that and she will note down. Okay, and again she will send one more number, she will get something, right? Again she does. Let's say it is goes in a circle, let's say one iteration. Alice picks a number, send it to Bob. Bob finds f of x, send back to Alice. So one complete round, let's say, equal to 1 iterations. So in general, how many iterations are required to figure out, right? Okay, how many iterations are required to figure out whether the function is balanced or not? For Alice, it would take, right? So at max, it would take, max means on her worst day, she would be needing 2 to the power of n minus 1 divided by 2. Sorry, 2 to the power of n by 2 plus 1. Okay, let me remove that. Okay, simple example we gave is if 2 to the power of n is, let's say, 9 numbers, sorry, 10 numbers. Okay, so she would be needing 10 by 2 plus 1, that is 6 attempts or 6 iterations. Okay, required to find whether the function is balanced or not. That is a maximum. On her lucky day, maybe she may succeed in 1 or 2 attempts, because let's say on a lucky day, what can happen is, for x is equal to first value she got 0 back. Again she sent a next number, let's say 1, she got 1. Okay, so in that case what happens? Straight away she knows that it has to be a balanced function, because it is having 0 and 1. For a balanced function, for the half the set of input values it will be 0, for the another half it is 1. The nature of that kind of a function is showed up in first 2 attempts itself. Okay, right? So that means she has succeeded by luck. But on her worst day, the only possibility is to find in this many number of steps. Okay, there is no need to go beyond this number of steps, because let's say in the case of 9 numbers, okay, sorry, 10 numbers, she may start with x equal to 0, 1, 2, 3, 4, 5. Okay, so for the first f of x value is 0, 0, 0, 0, up to 5 inputs, she got 0 in return. The next one would dictate whether the function is balanced or not. Okay, if it is 0, she can simply say this function is constant. Okay, or if the value is 1, she can simply say, right, let me remove this. If the value is 1, she can say it must be a balanced function. Okay, there is no need to go beyond 5 because she already figured out by this point. Okay, right? So we need this number of attempts. If you use some the classical computing logic, okay, if you use some logic, you can reduce the number of attempts, this many number of attempts, to a smaller number. Reduction possible to a smaller number by some computing logic, any classical computing logic. Okay, right? So, but the question is, if you use quantum computing or information processing, quantum information processing, okay, right? So straight away, okay, if you use it, then you can find, or Alice can find, Alice can find the f of x nature in one step or one iteration, you may say one iteration, right? So that is interesting, right? So how it is done is, she has to send the information of x argument values in the form of quantum states. Okay, so the process involves whatever number she picks from 0 to 2 to the power of n, right? Okay, those numbers, right, 0 to the power of n minus 1, sorry, I remember, like, we are starting with the number 0 means we have to subtract 2 to the power of n minus 1. If you're starting from 1, then you can say just 2 to the power of n. Okay, so if whatever x value she picks, okay, so takes them, Alice has to put them into a quantum state. Okay, right? It is possible, by the way, you can embed the information of these x values into a probability amplitudes. You can choose any kind of information embedding, probability amplitudes, okay, and create a quantum state, right? So send the quantum state to Bob. Okay, as we know, Bob can have a quantum gate, okay, takes that values, puts into a quantum unitary function, okay, right? Okay, so he would process, let's say he would process in such a way, he will have some ancilla qubit, okay. So ancilla qubit is chosen in such a way, the information of query register or query register is transported to ancilla qubit, or the essence of query is transported to ancilla qubit. So there is some output he will get. That output he will send back to Alice. Okay, right? So Alice would assess the output, whatever she received, and let's say she will make a table, and you just feed it onto the table which she is making. From the table she assesses it. Okay, right? So yeah, I'm sorry, I sharing is lost. Okay, yeah, share. Yes, so I don't know for how long the date screen was lost. Okay, yeah, right. So I'll just rephrase what I was doing. Alice will pick the data. Okay, convert that to quantum state. The quantum information is sent to Bob. Bob would like feed the data to a quantum gate, and there is an ancilla qubit is there that takes the information of the query register, comes out from the gate. That information of output is shared to Alice. Alice will analyze. Okay, right? I see some questions here. Let me quickly check the questions. Okay, right. There is a question here. Nearby raise hand icon, there is a left on option, connect to the audio. Please click it. Okay, this is something to do with the problem. Okay. N by 2 plus 1. No, actually, it is n by 2. Yeah, you're talking in terms of yes. Yeah. So n, why I take a small n? Small n is number of qubits. Okay. Right. If the total data size is capital N, okay, which is equal to 2 to the power of n, we will do 2 to the power of n means, let's say I have a data size of 8, so I just simply need a 3 qubits. Okay, right? So let's say there is a 8 input values are there. How much time, how many attempts would be needing to find out whether the function is balanced or not? And the worst scenario, in this case, it would be 8 by 2 plus 1, which is equal to 5 attempts. Okay, right? So 2 to the power of n minus 1 plus 1, say if it is balanced or not, but to say it is constant or not, we need to do 2 to the power of n attempt times. Not required. That many number of attempts are not required. We just need the 2 to the power of n by 2 plus 1 attempts, which is like, yeah, you are saying 2 to the power of n minus 1, okay, plus 1 attempts. Is it right? Yeah, I think you are saying right. Yeah. And it is not 2 to the power of n. 2 to the power of n minus 1 plus 1 attempts are required. That is right. The second statement is not right. We need to do 2 to the power of n times. No, it's not there. Okay. The first statement is right. I think Matthew, whatever you were saying. Okay, if we add odd number of data, then how to decide half values? Very good question. Right? Okay, so that is the case. Okay, right? So yeah, in that case, what happens? You might lose one like you might need to do one more extra attempt. Okay, so let's say the input argument values are, let's say 9. 9 by 2 is what? 4.5. Okay, so as per our notion, 4.9 by 2 by 2 plus 1, right? Plus 1. So which is 5 plus 1, 6 attempts. So you would need 6 attempts. You would make 6 attempts. There is no other go, because on the worst day there is no half attempt, right? Okay, right. Okay, so my question was, what if the function is neither balanced or constant? It will not happen. Okay, so Bob was asked to either use a balanced function or constant function. That's all. So Bob has no freedom to choose whichever function you want to use. Right? So that is understanding between Alice and Bob. I understand your question saying, so the function is, let's say for this case itself, okay. So for this, no, for the previous case maybe equally, right? So for this case, okay, so 2 times it is 0, and every time else it is 1. Okay, so this is either balanced or it is okay, either balanced or it's a constant. So that kind of a freedom is not there. Okay, right. So any other questions? If 2 cap n is 8, 2 to the power of n is right. Yeah, there is only 2 cases, either function is okay. Fine. I think those are the questions. So let's get back to the session, like a good part of the discussion. Okay. Now, what should be the circuit would look like for the Bob to process the information. Okay, right? So we just saw the Dutch algorithm circuit. Okay, right? So you would use the same Dutch algorithm circuit. Okay, let me draw the Dutch algorithm circuit for you. The same thing, you can always start with a quantum unitary function gate UF. Okay, so it will have two input arguments, sorry, two inputs, two outputs. There is a X, there is a Y. X goes out as it is, but Y changes by F of X. Okay, now the difference here is we need to add query registers, right? Query registers. Let's say there are so many inputs are there. Okay, let's say I have only one qubit. Okay, so how do I do? I simply give like this. Okay, right? And if there is only Ansela bit is 1, obviously Ansela bit is only 1 for our discussion so far. This is what it would look like, and there is a Hadamard here, a Dutch algorithm, Dutch circuit I am writing, and there is the output goes as it is. Okay, now the thing here, the change from Dutch algorithm to this case is Alice picks a number 0 to 2 to the power of n minus 1, any number, and send it to Bob. Okay, that is a classical way of doing. We are saying take all the numbers, take all, okay, sorry, take all the numbers, take all, convert to a quantum state, convert to a quantum state. Okay, wait a minute. Yeah. Wait a minute. Where is that gone? Okay. I did lose that. Okay, let me do the fresh one. Doesn't matter. We can draw it quickly. Okay. Okay, just a minute. Okay. Reload. I should click on that or close it. Yeah, I'm sorry. Okay. Okay, it is doing funny stuff. Cancel. Yeah. Keep. Leave. New. Okay. Yes, I get now. Yeah. Right. So Alice sends the 0 to 2 to the power of n set of x values. Now you see there is a lot of values are there. So those things are converted into quantum state. That quantum state is sent to Bob. Okay. Right. So Bob use the unitary function, takes that psi function, feed it to his unitary gate. Okay, right? Now y is chosen to be 1. Okay, that is one condition. And initially this set of values has to be like feed it to the system. So what you can do, you can start with all the zeros, n zeros, right? And take n Hadamards. We know that, we have seen that earlier. So just to represent, it is not a single line, you can just simply say, you write a cross line and say it is n, which means the one line is actually not just a single register, it is n registers are there. Okay, right? And at this point there is a n Hadamard's has to be there in the Dutch algorithm. Okay, this is the circuit would look like for Bob. Okay, right? So remember, we saw earlier, this stands for a quantum input state. Okay, input would look like 0 0 0 0 n times, okay, tensor product with 1. This is what the input which is going into the circuitry. Okay, right? So the moment we have Hadamard's acting, n Hadamard's acting on n0 registers, okay, and one Hadamard acting on the ancillary register, okay, we would get some new form, which is, you can say, just a psi1, right? Okay, right? So what would psi1 would look like? If you see carefully, earlier we derived this. One Hadamard acting on 0 gives me equal superposition of 0 and 1. You can say 2 to the power of 1, where n equal to 1 qubit. N equal to 2 Hadamards acting on 2 qubits. Both are starting in ground state, going to give me equal superposition of 4 substates. Okay, which is square root divided by square root of 2 to the power of 2. This is a state. Okay, which in short you can write it as summation over x belongs to 0 comma 1 tensor square x divided by 2 to the power of 2. Okay, so in general Hadamard, n Hadamards acting on n0 bit states, you can simply write it as summation over x belongs to 0 comma 1 tensor n. Okay, remember 1 divided by square root of 2 to the power of n x. Okay, remember. So by the way, what is x would look like here? X would look like 0 0 0, all zeros n times. So on, x would look like 1 1 1 n times. Okay, right? How many such states are available? 2 to the power of n states are available. Substates, or you can say substates. Okay, right? We know this is the one, this is the state which is going into the unitary functional gate. Okay, so at this point, after the unitary functional gate, let's say I have a psi2. Okay, right? So let's come there. Psi2 is equal to, remember, unitary function acting on psi1. What is, by the way, psi1? Psi1 is, okay, I'm sorry, there is something I have missed. Ancilla qubit I have missed. Okay, so I have to add the ancilla qubit also. Okay, psi1 is not only Hadamard here, there is a Hadamard acting also in the ancilla. So this part I have to also add here, which is inner product of, sorry, superposition of 0 and 1 with a negative sign. Okay, so this is what our psi1 is. Remember always to not to ignore the ancilla part. Okay, so now we have to find unitary action on summation over x belongs to 0 comma 1 tensor n. Okay, 1 to the power of 2 to the power of n square root x cat and 0 minus 1 divided by square root of 2. This is this state. I want to find unitary function. Okay, unitary action. If you remember correctly last time, okay, when we were trying to do, okay, right, whenever I have such an input for unitary function, the output would look like, you see, output would look like this goes and acts on this in combination on to this. Okay, the result is just the same summation 0 comma 1 tensor n minus 1 to the power of f of x. Remember, yesterday we derived that is Friday. Okay, everything else would remain the same 2 to the power of n and 0 minus 1 divided by square root of 2. Okay, so I hope you guys remember this function, sorry, this output. If somebody wants how it is, you can always reduce the system to simple case. What is that simple case is? Okay, reduce the system to n equal to 2. Okay, not n equal to, maybe n equal to 1 is the easiest way. N equal to 1. N equal to 1 case, what is the psi 1 would look like? Psi 1 would look like, you see carefully, x belongs to x belongs to 0 comma 1. Tensor 1 is just 1. 1 to the power of 2 to the power of n is just square root of 2. X cat 0 1 divided by square root of 2. Okay, now I want to find what is a psi 2, which is unitary action on psi 1. Okay, as we know, the unitary action on psi 1, the function is like this now. Okay, right? If this is x, if this is y, right? If x goes as it is, y plus f of x, this is what I have. Okay, right? So which means you can pick for the case of x being 0, y being 1. Okay, so that means you would be getting here, so let's say the output would look like 1 by square root of 2, right, minus x minus 1 to the power of f of x 0 minus 1 to the power of f of x 1. This is what you will get. Okay, you can, sorry, this 2 is 1 2, we have to remove 1 out. This is what you will get. So literally, which is equal to psi 2 is equal to minus 1 to the power of summation x belongs to 0 comma 1 minus 1 to the power of f of x 0. There is a square root of 2 here also. I'm sorry, I should have it here. Okay, this is what you will get. So I'm writing in general this output. This output I'm writing in general. Now, as per the circuit, let's get back. It's very, very important. Now there is a Hadamard acting on the query register. Okay. Now, how to deal with that? That is very, very important task. Okay. A Hadamard acting on the a query register, so that you have to understand very, very carefully. Okay, right? So let's keep this final psi 2 aside. Okay, this one, keep it aside. Try to analyze few things and then we will get back. What is the, see, psi 3 I want to find now, psi 3. So after the query register Hadamard, I will get a psi 3. Okay, I want to find what is this. Okay, right? So psi 3 is Hadamard n Hadamards acting on psi 2, or you can also say tensor with identity on psi 2. What I mean is, on ancilla qubit nothing is there, that's why I put identity. This is on the query register. Okay, this is on the ancilla register, right? Okay, so psi 2 is there. So carefully take the psi 2. Okay, just take side 2, right? First of all, I want to find Hadamard action on side 2. Okay, right? So best way to do is simple scenarios. Okay, so what simple scenario? Let's choose simplest case. Okay, right? Simplest case I'm choosing. Yeah, the simplest case we will be choosing is, I just check the chat message if some questions are. Let's choose Hadamard acting on X. Okay, right? As we know, if X is equal to 0, what it implies? H acting on 0 gives you equal superposition with the in phase 0 ket and 1 ket, no relative phase between them. Okay, let me write down that as some short form or generic form. What I mean is, well, I want to write in summation. Okay, I have already used the variable X, so I'll use some Z variable, nothing to do with the Z gate. It's a Z variable, belongs to 0 comma 1. Okay, I'll write it as Z ket divided by square root of 2. Okay, see, whenever Z is equal to 0, I'll get this input. Whenever Z is equal to 1, I'll get this input. So I'm just summing them. Summation is there, so I'll take that case. Okay, now choose if Fx is equal to 1. Okay, so in that case, what will be the action of Hadamard on 1? As you guys know, 0 minus 1 divided by square root of 2. Relative phase is there, out of phase, both of them are 0 ket and 1 ket are out of phase, 180 degrees out of phase. So if I had to write down a summation just like the previous case, okay, what I will do this time is, I want to have a minus sign for the second 1 ket. So what I'll do, I'll say minus 1 to the power of z ket divided by square root of 2. You see now, whenever is z is equal to 0, minus 1 is not coming to the picture. So I'll have 0 ket. Whenever z is equal to 1, I'll get minus 1 ket, minus 1 to the power of z. So minus 1 to the power of 1 is minus 1. So I'm getting that. Okay. So that means I know how to summarize action of Hadamard on x equal to 0, action of Hadamard on x is equal to 1 ket. This is what two outputs I would get. Okay, now let me generalize for any x. This is very interesting. You see, for any x, I want to do this time. Let me write a shorthand notation. H acting on x is equal to, carefully you see, summation over z belongs to 0 comma 1, okay, minus 1 to the power of x into z, okay, z ket divided by square root of 2. I am writing this way. Okay, right? This is the shorthand notation or summation or summarized notation I'll get. Okay, if you want to cross check whether this form is right or wrong, whether this is right or wrong, if you want to cross check, let's choose it for x equal to 0. X equal to 0, minus 1 to the power of 0 into z. So 0 is there, so minus is not coming into the picture. So the first case is coming. This case is coming. These two things will be outputs. When x is equal to 1, you see minus 1 to the power of 1 into z, the second one is coming. Okay, so both of them are captured in this one single statement. Okay, right? So very good. Now you might feel uncomfortable when I go for n, when anybody can go for n equal to, let's say, 2 or more. Okay, 2 or more query registers are there in that case. In this case, what happens? You see carefully, H acting on X, summation over belongs to 0 comma 1 tensor square minus 1 to the power of x into z divided by 2 to the power of 2. This is what the output would look like. By the way, how to understand this? Okay, so there is only x is one. Usually our psychologically we intuition is, whenever I say x value is argument looks like as x, it is a single value. Okay, so it is very difficult for us to see. Okay, what is 0 comma 1 tensor square is what, which is 0 comma 0 0 1 1 0 1 1. Okay, now I am saying x would look like or belongs to this set, which means x can take 0 0 or 0 1 or 1 0 1 1. Okay, so to make our life simple, right, what I will do, I just write x as something like x1 x2, just like some kind of a vector, but not a vector. Vector means two-dimensional vector means two input argument, two arguments are two coordinates will be there. Like vector r would have xi plus yj. We will represent r vector as x comma y points. Okay, that is what in general we will write. Okay, so for this case, let's say something analog to that, but not exactly that. So x is x1 and x2, where x1 and x2 it's like two coins tossed. Both the coins can be head, both the coins can be tail, or one coin head, another coin tail. Head and tail, both can be tail, like that. Okay, so I am doing for x. Similarly, I have to do for z also, because you see z also belongs to 0 comma 1 tensor square. So that means z is also z1 comma z2. Okay, right? So this is how you can bring some kind of a easy way of writing things so that you would understand easily. Okay, so right now let's take h acting on, okay, x1 comma x2. Okay, right, for n equal to 2 case I am talking about generic case. Now here, as you know, x1 comma x2 would look like 0 0 0 1 1 0 1 1 na? Okay, right, let's choose, let's choose for one of the case, h acting on x1 tensor, h acting on x2 tensor, x2. As we know, let's get back, x acting on, where is that, somewhere here we did, h acting on x gives me this thing, when x is a single input or single argument value. Okay, so only difference there to here is x is replaced by x1, so I can simply say, right, h acting on x1 would give you, okay, it will give you a summation z1 belongs to 0 comma 1. Okay, z1 belongs to 0 comma 1. So x1 is a single argument, so you'll have 1 there, so no tensor product there. Okay, I need to refresh, reload. Okay, wait a minute. Strange, I'm losing that notebook so quickly. Very bad. The systems are like this. So sensitive. Touch screens are so sensitive. Okay. Right. So what we are trying to do, we are trying to do h acting on H acting on x1 tensor, H acting on x2, which is summation over z1 belongs to 0 comma 1. Okay, cancel, cancel, 0 comma 1. Okay, so this would be minus 1 to the power of x1 z1 z1 cat divided by square root of 2. This is one input, sorry, one, this correspond to this, multiplied by like tensor multiplication. Again, z2 belongs to 0 comma 1 minus 1 to the power of x2 z2 z2 cat divided by square root of 2. This is what I mean. Okay, right? So my notes is lost, so let me show you from my notes what I mean. Where is it? Yes, yeah, here. Okay, so we just used h acting on x as an expression with minus 1 to the power of x into z. Okay, so that is what we were using here. Okay, now if you just put them all together, h tensor square acting on x1 x2 would look like, now you see carefully, I'll put two summations together, z1 comma z2 both belongs to 0 comma 1 kind of a thing, minus 1 to the power of x1 z1 plus x2 z2. Okay, z1 tensor z2 divided by 2 square. Okay, right? So you see, this is very, very important. Now I can generalize for any case. What is that generalization is? H acting on n times h n h acting on x1 x2 xn would look like z1 comma z2 comma so on up to zn, which belongs to 0 comma 1 type. Okay, minus 1 to the power of x1 z1 plus x2 z2 up to xn zn, z1 z2 so up to zn divided by square root of 2 to the power of n. Okay, so Hadamard's acting on, okay, a superposition, a state with n bits where each bit can be anything. It's like if I have n coins flipped at a time, n coins flipped at a time, all those coins were represented by x1 x2 and xn. Now if we say I send some kind of a disturbance, some kind of a wind onto the sum of the coins, like all the coins, if I send a disturbance, what would be the output would look like? It's like you have a quantum coins flipped, like atoms made to exist in superposition, n atoms are in superposition, they're making a flips. Okay, it's like one atom doing the oscillation, another atom doing the oscillation. Let's say this is x1 atom, x2 atom, so xn atom oscillations it is making, Rabi oscillations. Now I send a set of 5 photon. Yesterday we talked about area of the pulse. So, okay, so many photons I say sent to each atom, and I am going to see what is the effect. Okay, so that is what Hadamard's acting on, n Hadamard's acting on n coins. Okay, right? Now why do I need to know this? Because as part of our quantum circuit, let's get back, let me show you the quantum circuit. This is a quantum circuit. Okay, at this quantum circuit I just got what is the psi 0 would look like. Okay, what is a psi 1 would look like, what is a psi 2 would look like, and now I want to find what is a psi 3 would look like. Okay, so if you cross check, Psi0 is just 0 and 1 when I have only single quick register. If I have two registers, query registers, okay, in that case the query register would be having 0 0 initially, then two Hadamard's acting, it is going to create equal superposition, okay, and then one Hadamard acting on the ancillary register, and both together create a psi1. The psi1 goes through unitary function, and from the unitary function you would get the result output as minus 1 to the power of f of x x cat divided by square root of 2 to the power of n, and some 0 and minus 1 divided by square root of 2. This is what the output you would have after the unitary function. Now you have after the unitary function, what is the output? I know now. Okay, what is the psi2? I know, right? Which would look like, right? I think x belongs to 0 comma 1 tensor n. Okay, okay, let me exactly get what is a psi2, not to make any mistakes. Where is that? Yeah, here. Where is that? Wait a minute. Yeah, this is a psi2 for you. Okay, right? Minus 1 to the power of f of x. Okay, now I got that. Minus 1 to the power of f of x cat divided by 2 to the power of n. Okay, 0 minus 1 divided by square root of 2. This is what x2 is. Now I want to find Hadamard, n Hadamard acting on one identity acting on psi2. So this identity would go and act on this, but Hadamard go and act on this. Okay. Just now you got Hadamard acting on such x gives me the output like this. Okay. Right. So it is very, very important to just follow. You remember, you just see. Okay. Let me reduce. Hadamard, n Hadamards acting on the x gives me output like this, what is there in this box. Okay, right? So let me write down now carefully. Psi3 is, okay, Psi3 is, okay, right, x belongs to 0 comma 1 to the power of n minus 1 to the power of f of x divided by 2 to the power of n, n Hadamard's acting on x, okay, tensor product, identity acting on 0 comma minus 1, okay. This is what we have. Now we know what is the effect of this one. What is the effect of h acting on x state? So that is looks like this. Okay. Now let me write down that now. X belongs to 0 comma 1 tensor n minus 1 to the power of f of x divided by 2 to the power of n. This is z belongs to 0 comma 1 tensor n, okay, minus 1 to the power of x1 z1 x2 z2 so on up to xn zn z1 z2 so on up to zn divided by square root of 2 to the power of n. Okay, so this is what this effect. Now this one is there as this. This is very, very important. If you follow this, it's straightforward. Okay, right? So in short, usually x1 z1, x2 z2, xn zn. This would look like, let's say I have two vectors, analogous situation I'm talking about. Let's say there is one vector xi plus okay, reload, okay. Yeah, I think I lost that also. Right. So where we are at, again, I'll use my hand notes. Yeah. Right. Yes, we are at this position. You see, I have overall state psi3. Okay, wait a minute. Okay. Overall state psi3 would look like, where is psi3? Psi3. We can give a break now, I think, quickly. Okay. Okay, so let's give a break. Meanwhile, I'll make some equations ready which were just disappeared. Okay. If somebody wants to hang by, they can hang and ask any questions if they have. I'll just put up the equations again neatly again. Okay, so we'll take a quick 5 minutes break. 3:05 and then we'll come back after 3:10. Okay, go ahead. We have x, y, x, y plus f of x, unitary function, n had a mods, 1 had a mod, n, this is n, all n zeros, 1 0, 1 sorry 1 1, and there is n had a mods. Okay, and nothing here. Right, so this is a gate. Let me write down what is a psi 0. Psi 0 or psi input is 0 to the power of n tensor 1 kept. Why this is happening? System is becoming cancel. Yeah. Okay. Now psi 1 is n Hadamard's acting on n zeros and 1 Hadamard acting on 1 ket. Okay. So as we know, n Hadamard acting on n zeros gives me a equal superposition of all x's divided by 2 to the power of n. Okay, where x belongs to 0, 1 tensor n. Okay, right? Okay, so psi 1 I know, which is summation over x belongs to 0, 1 tensor n. Okay, x belongs x divided by 2 to the power of n, 0 minus 1 divided by 2. Okay, psi 1 we got as per the circuit. Now we will have psi 2, which is n Hadamard, psi 2 is unitary acting on psi 1. Okay, so unitary acting on psi 1 gives me summation over x belongs to 0, 1 tensor n minus 1 to the power of f of x, x ket 2 to the power of n, 0 minus 1 divided by 2 to the power of n. Sorry, not 2 to the power of n, just 2. Okay, the psi 2 we got. Okay, now psi 3 is Hadamard, n Hadamards, and one identity acting on psi 2. Okay, by the way, that it would be psi 3 would be summation over x belongs to 0 comma 1 tensor n minus 1 to the power of f of x h n Hadamard's. Okay, acting on x divided by 2 to the power of n square root 0 minus 1 divided by 2. Okay. By the way, h acting on x is equal to z belongs to 0 comma 1 if yeah.
Kindly take 5 minute break so that we can
Yeah, we
check.
are taken break. I'm just deriving for the next half of the session.
Okay, okay, sir. Okay.
Yeah, please carry on. Yeah, there is a question here. Why are we using Hadamard identity gate while tensoring with Hadamard? It is not necessary, right? Because after UF gate, we are applying Hadamard on query qubit alone. I have this doubt. I mean, why identity gate on Ancilla? Okay, right. So usually in quantum computing,